All right, hello everyone. My name is Sergii. I'm a co-founder at Kamu. So we're in the business of structured data and bringing structured data to Web3. And let me tell you what, I guess structured data is well understood, right? Not everything is an image, but what Web3 data means to us is the following. Starting from late 70s, the first SQL database was developed. Later, it took a very winding path through data warehouses. We then got MapReduce, transformed into data lake architectures, then pretty complex federated data architectures. But one thing didn't really change is that all of the structured data was really confined to the boundaries of one single organization, right? All of these enterprise data solutions are confining you to work only on the data that is coming from within your business. So what Web3 data means to us is breaking this boundary down. So basically migrating over to the space of decentralized data supply chains where data can freely travel between boundaries of multiple organizations, where you have micro-publishers like on the level of a single IoT device or a person supplying their personal data to the network. We have multilateral data contracts and data transformations, basically multiple parties engaging in really complex behaviors of exchanging data for mutual benefit. When we have decentralized analytics, being able to run your standard analytical workflows, but on the data that sits in completely different data sources. And ultimately leading to what we think is the holy grail is the collaboration on data, being able to collaboratively build these complex data supply chains. So this is gonna be a fairly technical, but very like sort of building up from fundamentals. I wanna show you what we think is the proper way to do structured data in Web3. And treat this talk as just as an invitation for further conversation about how we can standardize on all this stuff. So I'm gonna start with logical data models, basically what we actually put in these databases, what form of data we want to be there. So I'm gonna start really early, basically for like a lot of you probably took introduction to databases course in universities. So this is where I'm gonna start because I think we get off track pretty much immediately from that point. Because in those courses, we mostly talk about non-temporal data models. So like this table of account balances, right? You have account 1 with a balance 200, account 2 with a balance 300. These are non-temporal models because they don't have a time component to them. They only store state and evolve through CRUD queries. So this is kind of a historical how it came to be because databases mostly evolved in the context of OLTP, right? You have your application with a bunch of clients in it, interacting with the application as an engine of your business rules, and these rules are being translated into state transitions and stored in a database. Kind of an unfortunate feature of this entire model is continuous history loss because you cannot tell what your data looked like before the last transaction. So the DB is non-temporal. Then comes analytics inevitably. Everyone encounters this, like you ship your app and suddenly you face questions. How can I tell how this app is actually performing? Like what's the retention of a user? What's the like weekly active users I have? To understand that, we need to be able to ask questions from our data, like what changed, when, and why. And analytics is a historical problem. It's a temporal problem. It needs history. So we have to reintroduce time somehow into our data models. And this tiny yellow box there is probably derailed data engineering for decades, just figuring out what needs to be inside of that weird little box. Because we're suddenly in a space where we lost temporality, but we need to reintroduce it. And we came up with a whole bunch of different methods to do this, and they were very impactful on both sides, on LTP and analytics sides. But I'm gonna focus on two most prevalent ones right now. As first one is change data capture. So CDC is a very simple idea. Basically imagine putting a trigger on your database, and every time something changes, you immediately log it into some stream. So you have this type of CDC stream table where it says that account 1 at event time T1, there was first insert into this database. The data row was created. Then through series updates at T2, at T3, its state evolved, and now it's finally got to 200 balance. So it answers the questions of when and what. It doesn't, however, answer the question why, which is a very important question. Because CDC data is anemic, right? When you look here, you have inserts, updates. There's no such thing as insert and update in your account processing systems. There might be credit and debit, but there's no such thing as update. Like, what does that even mean? So it doesn't speak the language of your business. It puts you in a position of reconstructing why and what, which is often impossible because information loss already occurred. But very many people and many companies try and get stuck in these problems for decades. A very much superior model is event sourcing. So this is a software engineering term, but the key idea here is let's treat state as just a projection of event history. So if we have event log, this event log can speak the language of your business, having debits, credits, transfer, purchases, and then you can materialize the state on demand, and the state can be computed in variety of different ways. Right? It can be a projection of account balances, but it can also be the amount of SKUs that were purchased in total, etc. So event sourcing plus CQRS model gives us this very nice path where we suddenly don't lose temporality anymore. Application stores their data in event store. You have projections that still compile it into the state for very efficient querying, but analytics can just source the data directly from an event store without any need of reconstructing anything because everything stays temporal throughout. So you might be wondering, why am I telling you this? Isn't this just like a blockchain type of model, right? And there's 2 points. I see too many Web3 projects still use CDC model as their starting point. And I believe this is just a time bomb because right now we're building applications on Web3, but inevitably we're gonna run into analytics. Like projects like Dune Analytics, they're already doing a lot of, giving you the tools to do analytics on blockchain data, but a lot of this data is still in the CDC format. You cannot figure out what happened or why something happened from the CDC. And a lot of smart contracts don't emit logs properly, so we still depend on some data about state changes of individual variables that often is not very useful or really hard to figure out why from this data. So I think even L1 developers can actually learn a lot of new things from event sourcing model, making events like a primary data on L1s. The second reason I'm telling you this is just to show that OLTP already loves event logs, right? OLTP is converging on these append-only ledgers that are super nice for us because they both can bring dynamic data, but also content addressable data. So on the right, I have here an image how this event log could be materialized in IPFS, ignoring the actual physical layouts. So we can just have a bunch of CIDs that just evolve one from another. So data is both content addressable and evolves over time. It's history preserving, which is great for accountability, verifiability, etc. So this is the logical model, how we now map this model to actual files or what's going on, like what are we even putting into our storage. So again, a lot of evolution over decades here, starting with monolithic databases that just handled all of the aspects for you, right? They bring some proprietary data formats. They maintain indexes as part of those formats or separately. They bring the querying, query scheduling, query execution models. So all in one solution, but it can only scale vertically. So once we reach the limits of the vertical scaling, we went to the database clusters, and suddenly you have petabytes of data in one database cluster in completely proprietary formats. And once you face the decision of you want to migrate to a different technology, you're stuck because your data is in this highly proprietary format and highly proprietary solution. So this led us to data lakes, which sometimes are described as deconstructed databases. So the key idea here is that let's separate the data and store the data basically in individual files. It can be CSV or JSON, what have you, and then just have a layer of compute on top of it. So some scheduler that can schedule data processing tasks on top of the data. So this allows you to run multiple such engines, like some might be specialized on processing GIS data, some might be specialized on just pure analytical processing. So it gives you an ability to easily switch from one engine to another while your data stays mostly static. It's basically a data-centric design. The question here now, we kind of lost the indexing part, right? How do we make this actually perform well? So this is where big data formats come into play, like Parquet, we've seen in a demo today. They bring compactness to the data, and they also bring fast querying, because in formats like Apache Parquet, they're columnar, and they also have built-in indexes that allows you very easily to search through data. They're also very friendly to compute, because you can actually like memory map it into RAM, or even memory map it into GPU directly and immediately start running your computations without any transcoding going on. So technologies like Apache Arrow that specialize on this make compute really, really fast. A key property of them is also that is very relevant to us is that they're immutable, which is very interesting, I think. Because now we suddenly have these data lakes evolving by adding more Parquet files, right? This is another indication that all labs have event logs. And enterprise data is actually much closer to Web3 than you might think, because data lakes are already becoming these event ledgers. There are some solutions that are trying to bring CRUD to data lakes, but I think it's really a step back towards CDC model. So I think they're addressing immediate needs of their customers, but it's not really a very well thought out long-term solution. But really, I see that Web3 data can really be a continuation of this deconstructed database model. We don't really need a hard break here. We can already meet enterprises where they're at right now and start layering the properties of Web3 data that we want to see to enable these decentralized exchanges on top of the data that already exists in their data lakes, right? If you have big organizations storing their data in S3, they might be comfortable with it, and we should support it to allow them really easily expose their data without forcing them to copy all of their data into IPFS suddenly and maintain these two distinct copies of data. So there's a really big missing piece, like Web3 dataset shouldn't be just a bunch of Parquet files in IPFS. We need an ability to represent some higher level constructs like schema evolution, because if you have a data set that is long living, there's very likely that requirements will change, the data set is going to evolve. We also need compactions, like there's a lot of maintenance to these Parquet files that needs to happen. Partitioning needs to be accounted for as well. So we really need a metadata standard, and this is going to be essential for us achieving interoperability in Web3 space to get into the place where data lakes are already, like where you can have multiple engines running on the same data. We need the same ability for Web3 data as well. So I think agreeing on a metadata standard should be our #1 priority. And enterprises, unfortunately, doesn't have a good answer there. There is no like really a good metadata standard as far as we can see. Before I get to the solution to this problem, I also want to touch on processing models. So once we have this giant Web3 database, what processing model should it have? And I'm not talking really about like what query language it uses. It's really like a minor detail, but rather how it executes these queries, right? And for a lot of you, it still might be confusing what I'm talking about here, because 99% of data processing right now is batch processing. So you might be only familiar with this model, right? When you use Excel, you're doing batch processing. When you're using most of the databases, like through SQL, SparkQL, any kind of query language, you're still doing batch processing. Same with pandas and R frameworks like Hive, Impala, Presto. Everything is batch, surrounds us. The key property of batch is that it treats data as a bounded list of records. So when you execute a query, it goes to that list of data and it runs your query from start to finish, and only after that gives you the result. So to illustrate why batch is not enough, I want to give you an example. Like imagine we have a data set of hospital admission records, and we want to calculate daily number of COVID-19 cases. You might imagine running this SQL for this purpose, right? We have a really simple select with group by date, and we're counting the number of cases per every single date. And let's, since it's a batch, we're gonna just agree to execute this query every midnight. So to show you how batch performs in this scenario, I'm going to use something called Bitemporal Diagrams. No need to panic here, it's really simple. So on x-axis, we have event time. So this is when event actually happened in real world time. So for example, one case of COVID was registered on midday on Thursday, right? System time is the time when this event actually made it into our database, into our system. So this diagonal that you're seeing here, it basically represents the ideal case. Whenever something in real world happens, we immediately know about it in our system. So in this idealized case, if we run this SQL on Thursday midnight, we count the number of events, we get 2. On Friday, we get 1, but also 2 because with batch, we constantly reprocess our old data. So this looks good so far. There's definitely like this inefficiency going on because we're recomputing the results over and over, but whatever, like it looks okay. It's workable. However, when you encounter the reality of data, you suddenly get a lot of interesting problems. Like your data can be late, it can be out of order, it can be lost and then backfilled several days after. It can be run and then corrected. And people often refer to these as like edge cases, but they're not really an edge case. Like this happens to data all the time. So in BC province of Canada, where I'm from, this is how COVID-19 dataset actually looks like. On Saturday and Sunday, we don't get any data entry because I guess that person who enters these records in the database just like sits at home on the weekends, so you don't get data on the weekend. There can be a later night shifts at the hospitals where data gets entered only on the next day, right? So data is delayed. If we start running batch processing on this type of data, on Thursday, you immediately get an error. You get 1 instead of 2. On Friday, you get 0. There's completely like wrong results for several days going on weekends. So there's 2 problems here. Like we're getting wrong results on dynamic data, but even bigger problem here is that we're actually rewriting history. Every time you ask batch, give me this computation over Saturday and Sunday, it potentially can give you completely different results, and it's not made explicit that it's doing that. So can this be fixed somehow, right? Well, maybe we can delay processing by 1 day, except on weekends. There we probably need 3 days. Oh, and there's probably statutory holidays. We don't have the statutory holiday in our data set yet. We don't know how it affects us. So this is a lot of cognitive load. And if you start accounting for all of these edge cases, you're definitely going to make a mistake in your SQL. And this is just for one data set. Like it's a really simple query touching one data set. Imagine if you need to join 2 data sets that are constantly out of sync of one another. It just becomes like such a more complex problem. So the reality of batch, how we see it, it relies on data completeness, which is not the case most of the time. It basically wants you to stop and wait for all the temporal problems of data to disappear before you start processing, and pushes all this complexity onto you. Like you need to figure out whether your data is complete or not. And this makes all this processing very manual. If you as a maintainer of this data pipeline walk away, basically the data stops flowing immediately. And this is what we saw with a lot of COVID-19 data projects, is as soon as funding dry up, or like the interest in the problem slightly goes down and suddenly you don't have thousands of volunteers working on this problem anymore, pretty much every COVID-19 data project died, which is really unfortunate. So when you're using batch, especially on dynamic data, you get non-reproducible result and correctness issues that undermine trust in data, trustworthiness of data. And it's also non-composable, right? You can imagine this arbitrary 24-hour interval working out within one company, but when you start trying to develop a proper data supply chain that goes through multiple actors, suddenly they have to coordinate on these intervals somehow. Like it's just unimaginable for you to actually build out something reasonable from this type of primitive. It's also inefficient, yeah, as I told, on recurrent tasks. So here enter the stream processing. This is a different model, and it treats all the data as an unbounded stream of events. So processing can actually run continuously and potentially forever. There is no such thing as done state. Results are emitted throughout the processing loop. it's very new, so like the third generation stream processing engines right now are represented only by Apache Spark, Flink, and differential data flow, which is also part of Materialize engine. So they're still actively evolving. This is how the stream processing framework would handle this complex case. It would basically emit one result per day. It would not reprocess the data. It just continuously follows. And this magic green line would somehow figure out that, okay, on Saturday and Sunday, we probably don't have full picture of the data yet. Therefore, we have to wait until like late Monday to actually emit some kind of result. And this magic green line is the cornerstone of stream processing. It's called the watermark. And it basically tells us so watermark at time, system time S and event time E tells us that with high probability, the system observed all the events prior to event time TE. So here, for example, on Saturday, with high probability, we observed all of the events from Saturday only later in the afternoon on Monday. So watermarks are really cool because they can be, have multiple forms. They can be predictive, so based on observed delays of the system, right? It's a probabilistic model that your system can adapt to the latency of the events arriving. It can be manual, like we can just set a fixed offset and say that, yeah, 24-hour delay is good enough. But most realistic, I think, it can be set by a maintainer. So a person doing the data entry in a hospital can you provide you this off-band data saying, I finished the data entry for these dates. You can now continue with your processing, and with high probability, your results can be consistent and correct. So I think stream processing is a super honest model that highlights that data processing is always a balancing act between correctness and latency, which I think is a really important concept to understand. Because what I see is there's a lot of sentiment going around saying that, well, batch is for static data and streaming is only for dynamic data. But I think it's a fallacy, because I see stream processing as a superset of batch. It's just a much more powerful and complete model that is useful for many types of data. And as we see, our data is becoming more dynamic. Like it started with financial data, stock market tickers. Now we have blockchains also as really highly dynamic data sources. We're moving into IoT proliferation and more of a smart cities use cases, where we're going to have millions of data sources, dynamic data sources that need to be processed. And even if, let's say, you do have static data set, right? It can be a data set of some, let's say, populations of Byzantine Empire cities. This data set still can be revised, right? There will be a scientist that is going to revise this data point. And now then it becomes a question of how many decisions have been made on top of this data set, how many other derivative data sets were created that take this as a ground truth. And really the difference between batch and streaming is who reacts to these revisions, whether it should be a human in case of batch, and do we really trust humans to do all this, or it's just a machine that emits a correction. So to illustrate, in our case, if we realize that some big chunk of data was missing on Friday and we later backfilled it, stream processing is going to automatically emit an explicit correction. So it's not going to lie to you and say like, oh, on Friday it was actually 4, I was right all along. It's going to explicitly tell you, remember Friday, I said it was 1, but it actually should have been 4 because I later got the events that confirmed that. So yeah, once again, I think it's a really honest processing model. And the model that addresses temporal problems instead of ignoring them, and gives you the control of the latency versus correctness trade-off. It's also really autonomous. You can basically write this query and leave it running potentially forever, and it's still going to produce valuable data for you. And it's infinitely composable, right? You can easily imagine this stream processing pipeline consisting of multiple stages, operated by multiple people, different organizations. They don't have to really care about agreeing on some synchronized processing intervals or some scheduling, right? It can just take care of all these complex problems for us. So if you're, just a really interesting comparison, if you've been writing smart contracts for blockchain, you've essentially been doing some stream processing already. I think in blockchain case, it's a much simpler case because blockchains are consistent and linearizable, and most of the real world data just isn't. The temporal problems immediately show up themselves once you start doing off-chain data or even just cross-chain transactions between blockchains that might be out of sync with one another. So to solve this problem, we created Open Data Fabric. And ODF is just an open protocol spec for decentralized exchange and processing of data. So you can find it on GitHub. It's just a document that we want to collectively evolve as a community that specifies all these things that I talked about, like data model, logical and physical, metadata format for how to represent structured data and how it can evolve. Processing frameworks of how do we process data while maintaining verifiability, accountability, provenance, and also identity and ownership component of it. So I'm just, in the interest of time, gonna give you some highlights of ODF. So first highlight is that there is two kinds of data in a system. Explicitly, we separate between source and derivative data. So source data, you can think of it something generated by system or as a result of observation. Like let's say you have a temperature sensor. This type of data cannot be reconstructed if it's lost. If you lose your temperature data, there's nothing you can rewind and look at the data in the past. That means it has to be durably preserved. Derivative data, on the other part, which I think is actually majority of data in our society, it's created from other data as a source by some sort of aggregation or summaries, some sort of function. So this data can be easily reconstructed if it's lost, assuming that the function that was executed is actually deterministic and that we can still reach that source data that it was pulling from. So this is how logically Open Data Fabric looks like. So on the left-hand side, we have our data publishers publishing the source data. We basically put these ledger-like requirements on top of their data set. And what this gives us is it establishes a trust anchor. All the data that you get from this type of publishers can be reproduced. It can be proven that it actually came from this publisher, and you can use these ledgers to hold the publisher accountable for all the pieces of data that you started using from them. Next, all these blue data sets are the derivative data. So basically think of them as these streaming SQL queries that continuously run on some infrastructure, producing new data. And this is basically a giant ETL data pipeline that can span multiple organizations. Like each of these derivative data sets can be operated and maintained by a different person, different organization. You can see that our system effectively removes people from the hot path of data. So all these scientists, analysts, they're configuring the system through these queries, but they never actually shovel data from point A into point B. They never actually touch data manually. Everything goes through the queries. Everything is codified. This creates two nice effects. First of all, this whole thing can be really highly dynamic and responsive. So any piece of data incorporated into a publisher here, it can immediately, thanks to string processing, propagate through the entire network and be incorporated into this much more higher level derivative data set that some decision maker are gonna look at from their dashboard, or some automation like a smart contract can be using to fire some triggers or do some high level decision making. And second property is that you get provenance. So any piece of data that you consume as this decision maker, any data cell can be attributed to the ultimate data publisher who provided this data, and you can see which transformations were applied to form it into its shape that it exists right now. So all of this is achieved thanks to the temporal metadata. So metadata is a crucial point of our system because it's basically a passport of the data. It records where data is coming from, how it was transformed, all of the aspects of how data looks like right now. And metadata is also temporal. It's a ledger because, as I said, these data sets can be long-living. We need some ability to evolve them over time. So do query changes. If your derivative data set needs to be modified somehow, do the schema changes. So yeah, this picture shows how these metadata relate to one another. So in a root data set, you can have data edit events, schema changes, etc. And in derivative data set, you can react to the schema change, which is also going to be captured in metadata, or you can change a query to accommodate for some, let's say, new columns that have appeared in the data set. We explicitly target any storage, like literally any storage can be used to store these data sets, because like I said, if an enterprise company is already comfortable in using S3 and want to continue using S3 because they're like have their Apache Spark and a bunch of analytics already working on it, we provide a format that you can use to materialize these data sets in S3. Similarly, there's a content addressable layout where these dynamic data streams can be materialized in IPFS, which basically looks like this, like these green rhombuses are metadata blocks, and these blocks can refer to files containing the data, Parquet files, and also checkpoints that allow us to resume the computations of the stream processing from any point in time. We're also agnostic of processing engines, so there's a plugin system, and we can support basically any data processing framework. We want to be very open to the types of framework that can be used in our solution. We currently limit ourselves only to stream processing engines, and this is not a technical limitation. It's basically to prevent our users to shoot themselves in the leg with batch processing, mostly. So right now we're supporting Apache Flink and Apache Spark streaming subset of the Apache Spark. So an engine doesn't have to be modified in any significant way to run as a subset of ODF. All of these properties like verifiability, reproducibility are layered on top of it by this coordinator process. So there's a very simple interface that you have to implement, usually through an adapter on top of the framework. And yeah, you can plug it into the environment. So while ODF is a protocol, Kamu is our product, which is our planet-scale data pipeline solution. The key product right now is Kamu CLI. We basically started building this from ground up and wanted to test our reproducibility, verifiability, and stream processing model within a simple tool that you can immediately use. So it brings you the simplicity of Git, but for data management. So you can already download it today, install it on your laptop, and build out a pretty complex enterprise-grade data pipeline. This data pipeline can be peer-to-peer, so you can like arrange a pipeline with your colleagues or teammates. And you get out of the box 100% verifiability, reproducibility, and automated provenance. So it's pretty cool, and it has a lot of like integrations like with Jupyter notebooks that allow you like really easily just explore these pipelines and navigate the data. So our goals for Kamu is basically make publishing as simple as possible and enable collaboration on data on a scale that we currently see in open source software. Like this component of verifiable trust, we believe that is the key piece that is missing for us to collaborate on data, but also shifting from batch to these stream processing workflows, it allows people to just work with data much easier with a much more concise code. So basically, you can collaborate on data pipelines code very similarly to how you collaborate on any open source library, which is pretty cool. Our goal is to bring fidelity of stock market tickers to all significant data flows, right? Why is the market data is the only real-time data source that we mostly get on our phones, right? What about unemployment data, decarbonization, like all these really important data flows of our society? Why do they still like shake up the stock market whenever some statistic comes up? Like unemployment data continuously throws the market off, especially during the COVID times, because we simply don't get dynamic access to this data. That's the only reason. And we are decoupling ownership from storage and processing infrastructure. So finally, a party that processes the data can be completely separate from the party that is a stakeholder that is interested to run this data transformation or owns the data set that they're publishing. So I think a real measure of a good design is how many things you didn't think of and later discovered and was amazed by like, oh, this actually works in this use case too. So I wanted to highlight some cool synergies. Like first of all, this whole idea of convergence of data that I've been hinting on, right? We looked at the state data, how it evolved through CDC towards event sourcing. We looked at the event data, how it was evolving completely separately from these engines that were doing mostly like time series processing, but now combined into this stream processing framework, third generation stream processing that can handle both of these use cases. A lot of synergies there was also in like intermediate stages OLAP, like bitemporal data, that was just too complex to grok when applied to batch processing. But with stream processing, it just makes so much sense. So I think like distributed ledgers are there as well. So I think we're really converging on something like I would personally call one true data. It's really starting to look very similar from all of the perspectives. We believe that this model can function very easily for on and off chain data in the same exact way. So blockchains are ledgers, right? And they already satisfy all the properties that we require ODF dataset to satisfy. So we can treat them as dynamic data streams. So using ODF with on-chain data, you basically can get zero copy processing. So some projects like Dune Analytics, for example, before they let you run some processing, they need to take blockchain, decode it, then put it in a huge database, index it, and only then they let you run queries. So this is not a very decentralized model because how many nodes on the network can handle these multi-petabyte data sets? It's going to be very few. So if you treat blockchain as a dynamic data source like dynamic stream, you can actually define your stream query and just say, I'm only interested in data from this smart contract, only in the change of this variable, and then you deploy this query immediately to the blockchain node, and it's going to stream this information to you. So this actually gives you like really low cost, near real-time data pipelines, but also with a trust anchor coming from directly from a blockchain ledger. There is no copying of data into some database that you don't really know the provenance of, or it's not really verifiable. You can trace the provenance exactly to the individual blocks of a blockchain. So this allows you to very seamlessly enrich blockchain data with off-chain data sources because they're part of the same model. So another thing I have alluded to is that derivative data is basically a form of caching, right? If you can reconstruct the entire thing, you don't have to store reliably all the derivative data. So storing derivative data becomes just a trade-off of storage versus latency. And this is how we can achieve the massive scale of collaboration at really minimal infrastructure cost. We also can get codified governance because our metadata chain can be extended. Like I said, it supports schema changes, but it can also support these notifications about significant retractions and corrections. So our background in DSci, we're coming from that angle. And I think it's really important for you as a scientist, if you started consuming some data set, build out a lot of research, publish your research on top of this data, and then suddenly you get a significant retraction from the source, that you will be notified, and it's going to prompt you like, hey, like the data set that you've been using for your project actually had some really significant changes, and you might want to revisit your project. So this really puts the all of the complexity can be codified in this type of temporal metadata, which I think is really powerful. Like same goes for all the license management and stewardship information, semantic graph, etc. It's also really helpful for systematization, right? Right now, we're just failing to systematize data, like all the data volumes that David talked about in his talk. Right now, if you go to any major university's data sharing portal, they're just drowning in the amount of data sets. And I think it's mostly because of our data science workflows. They're encouraging excessive copying and versioning of data. Whenever you consume someone else's data set, you're encouraged to make a copy, upload it into this research hub just to enable reproducibility through versioning. And this creates a lot of noise because suddenly you get a bunch of copies spread everywhere. You get copies of the same data set. Like it's just madness. So I think with ODF, we can really shift the focus towards let's structure all of our workflows around the set of core dynamic data sets coming from governments, coming from research, and then entangle them into these higher level data pipelines. So you get both long-living data sets that are a lot more easier to systematize than a bunch of copies, and you also get very transparent pipelines, right? It's a lot more easier to contextualize data once you see that it's already a part of some pipeline, and like this data set produced by MRI machine in this hospital is being incorporated into this global data set of MRIs, etc. And finally, an interesting observation is the relationship between ODF and Oracle networks, right? With ODF, what we're doing, we're basically moving the trust anchor from API call level, like in Oracle networks, to the data publisher. So we're allowing you to achieve reproducible querying of the data and hold all the parties accountable. So not only the publisher, but also the collaborators, people who might have processed this data through multiple stages, and also hold accountable the infrastructure providers themselves. So I think this really puts a big question mark on the future of Oracle networks, if we can achieve this type of model, because I think the verification of these streams is a lot cheaper and more efficient model than establishing this trust anchor through the consensus per every individual API call, like on most major Oracle networks. So this is the conclusion, right? Web3 data doesn't have to be a clean break. I think we can easily meet the organizations where they are right now and basically structure Web3 data as a continuation of many decades long trends. I would recommend to avoid CDC unless you know what you're doing. It's really a stopgap in most of the projects. It's not really a long-term solution. And consider batch harmful by default. It's useful in a lot of contexts, but really stream processing can serve a lot of these queries in a much more safe way. I really believe that stream processing is basically an ongoing silent revolution in data processing that is going to make a lot of our workflows less manual and more automated. So ODF, this is an invitation for standardization, just for us to organize and start defining how structured data should actually look like in Web3, because I don't think we can afford further fragmenting the space, right? We want data to be interoperable between multiple compute solutions. So really, after all the talks today, like what I see ODF becoming is really this layer 2 network, compute over data network, based on top of FVM or perhaps based on top of higher level primitives of Bacalhau. We have a lot of work to do still, like SQL over blockchain was one of them. Other types of proofs of the verifiability proofs. Right now we're basing everything on reproducibility and determinism, but obviously it's not suitable for some use cases. So yeah, thank you very much, and I hope to hear your feedback.
One of the slides you mentioned that 99% of the jobs are basically batch, and you mentioned towards the end that you think the future is streaming. How do you anticipate large companies or corporations that are mainly running batch jobs onboard themselves into this new streaming future?
It's going to be a slow and painful process because tooling is simply not there right now. Like I said, there's only 3 major stream processing engines, but I think really the pressure is on like a lot of data becoming more and more dynamic. And if your batch data processing pipelines continuously lies to you and actually produces non-consistent, incorrect data, the pressure is on the companies to do something about it. Also, Web3 is going to put a lot of pressure as well because, yeah, like I said, this simply is not a composable model, right? We need something that can be composed and layered on top of one another. There, please.
Have you looked into the Apache Iceberg project as a metadata solution for running compute over like Parquet files and data lakes?
Yeah, I've looked at the Apache Iceberg. It didn't immediately struck me as a fit because I don't think their metadata is temporal. I think it's more like a CDC, like basically CDC on top of the metadata, which is not something like what we want to achieve. We don't want diffs in our metadata. We want it to be basically also an event log that tells you how the stream is evolving, not saying like, oh, suddenly like the schema is completely different. How do you do that? We also want to enforce some really higher level rules on top of the metadata that, for example, does not allow you to create any kind of backwards incompatible changes to a stream, like dropping a column, for example, or like changing a data type of a column that would completely break your downstream consumers. So we're approaching the metadata design from the perspective, here's this long-living data set, and a bunch of people might have created data pipelines on top of this data set, and we want to minimize the impact of every change that you make as a publisher to these downstream pipelines to keep them going. Because if we start with any type of change, blowing up these pipelines and saying like, okay, this stream is over, here's the new stream, we're basically back to the batch model, non-composable model. So really, like with our approach to metadata, we want to encourage this long-living factor. And yeah, I am happy to be corrected wrong, and if the Apache Iceberg is a really right solution to that, I would love to hear about it, yeah.
Hi, thanks for the talk, that was great. You made a big caveat at the start about only thinking about structured data. Does sort of two-part question, does any of this kind of preclude semi-structured and unstructured data? And if yes, like what are the main challenges there?
Yeah, I was going to start my talk by defining structured data, but I was just, yeah, it's too much content for one talk. How I'm thinking about this, right, with all the cheese images in Web3, right, obviously image is closer to unstructured data than to structured one, right? Same goes for X-rays, MRI data, like there's a lot of, I would classify them as observations captured like over time or instantaneously, and these type of formats are mostly immutable. So you can think of them like how I represent them is kind of like a cell in this structured data set, right? And in our solution, we would simply link, like if you have a data set of images, you probably have some sort of metadata of what this image represents, where it was taken, some kind of geo coordinates associated with the image. So there's definitely a flow from unstructured to more structured, and we would like to use our solution to create these overarching data sets that describe the unstructured data stored probably directly in IPFS, and then just link to it, right? So a storage of images might evolve by just throwing more images into IPFS, but we still need some sort of overarching data set that tells you what these images are and how to find them, right? Like, why don't we have a data set that tells you about every MRI scan that was ever taken in the world? And this type of data set would be collaborative because there are so many data publishers producing this data. We need to bring all this data into one place to be able to discover it. And it would be highly dynamic because these type of data flows, yes, like one image once taken, it's static, but the data set of images being taken all over the world, it's constantly evolving. So this is kind of roughly how I draw the line between the two, is that metadata allows us to get a higher level concept of what is going on, and then you can drill down towards images or other unstructured data.
You mentioned Apache Iceberg. Are there any other projects in public, if you could wave a magic wand, that ODF would partner with, or I don't know, any thoughts about like how to go forward with lots of other people since this is such a common problem?
Yeah, so really want to be inclusive of all the data processing engines. The more we can get, the better. From the other perspective, I would really love to partner with something like Bacalhau, basically a compute infrastructure. Also, from the earlier talks with Fission, right? Like we need a common authentication authorization framework, which I think their solution would be perfect for this. So there's a lot of synergies going on, and we are explicitly want to minimize the amount of things that we reinvent, basically bring them to zero.
That's fantastic. Sorry to follow up, but I've seen similar things, and again, I think everything here is great, but like Open Lineage or like you mentioned, Iceberg, they're just, everyone's kind of taken a run at this before, and I wonder if there's someone to partner with, that's all.
Yeah, like Lineage, I think, is not a good stopping point. Like, it's not enough to know that dataset A was produced from dataset B. We also want to know the transformation that was applied. We also, like, ideally, we are pushing towards fine-grained provenance. So being able to query, like, oh, here's this data cell. I find this value kind of suspicious. Can you tell me where this value is actually coming from? So these are the types that, like, it's probably a handful of projects that can actually drill down into the scale, but we really want to pursue that. So, and it's mostly enterprise solution that, yeah, they can give you provenance, but it's only in your like very constrained use case,
Right.
which is not usable in Web3.
Okay. Yeah. Walid gets last question.
Thank you. Yeah, I just want to clarify one thing. You mentioned that batch is not accurate compared to stream processing. And I think the example that you mentioned is the utilization of watermarks, which is basically the distinction between the event time and the ingestion time or the arrival time.
Yep.
But that approach is not unique to streaming. It's also possible, or that's the logic also can be applied on batch processing, where you define the point of where you are more confident about the data that you're receiving.
Mm-hmm.
And technically with batch, it's actually more achievable and easier to achieve more accurate data because you're capable of doing more deduplication by partitioning the data and achieving higher locality. So maybe I misunderstood something about how streaming is more accurate than batch.
I didn't really get the last part, how you can achieve these things through partitioning. My main point is that with batch, it's on you to decide when to run your computation and how far into the data you want to look at, right? So in this case, if we run data processing on Sunday, do we want to include Saturday and Sunday in this processing, or we have to know that, oh, there's actually was no data input happening on these days, therefore we need to delay and only reprocess data from Friday. So this right now is completely on you in a batch processing world. There's no mechanism that will tell you that maybe you should hold on for a little bit because your data is not complete yet. So this is why you get a lot of inconsistencies in data and correctness issues because you're kind of running ahead of your data, which is super important when you start joining streams together. Like let's say you have a data set of your investment portfolio and you have a data set of the like stock market prices, right? And you want to figure out what's the value of your portfolio now. You might be refreshing your data set of the portfolio once a month. So for the duration of the entire month, if you approach it naively, you will get incorrect results because your original data set was lagging. So stream processing gives you this ability through watermarks to define how to know that your data set is lagging compared to another and delay the processing. Does that make sense?
Yeah, I mean, yeah, makes sense for the example that was given. Thank you.
Thanks.